Hello and welcome to this AQA Further Maths Statistics video looking at continuous random variables to linear functions of continuous random variables. First of all, a reminder of what you should recall from earlier videos, the definitions for the expectation and the variance of x, where x is a continuous random variable. And if you haven't remembered those, perhaps just jot them down somewhere for reference during this video. So we have looked at this in part earlier, but the general definition when we have a function of a continuous random variable x rather than just x itself for the expectation is the integral of that function multiplied by the probability density function. And you saw that in action when we evaluated ex squared as the integral of x squared multiplied by the probability density function. And what we're going to look at in this video is a linear function of our continuous random variable x, and that linear function is ax plus b. So recalling this result for the expectation of a function of x, that simply leads into the fact that e of ax plus b would be the integral of ax plus b multiplied by our probability density function. And that can be simplified by multiplying it out, and I think it's fairly easy to see that we can take our constant out of that integral and write it like that. And then we can add these two integrals separately, and we can write that as b multiplied by the integral of fx. And this, you should recall from when we looked at PDFs at the very beginning, the integral of a PDF over the whole range possible is always 1. So this simply gives us b, and you should recognize this as e of x. So just as we discovered when we looked at discrete random variables, for a continuous random variable the expectation of ax plus b is a multiplied by the expected value of x plus b. Now if we look at the variance here, obviously variance is much more complicated. So if you recall the definition for variance of x, this is using that formula, but rather than having x there, we have our function of x, g of x. And looking at that, when we have g of x as our linear function of x, I'm recalling the formula for the variance there. If we have the variance of ax plus b, we're just going to insert that for g of x in these two places. And then you may like to have a go at writing this out, and you will find that if we get going on this very much in the same way as when we did it with a discrete random variable, we will end up with this as our first stage of simplification, and then this will actually turn into, and I'll let you have a go at that, a squared integral of x squared f of x, which is clearly ex squared, plus 2ab integral, I missed the x out there, integral of x f of x, and that's just e of x, plus b squared multiplied by the integral of f of x dx, and we know that equals 1, and then minus a squared e of x all squared minus 2ab e of x minus b squared. And just as before, you'll find these terms cancel, and we are simply left with a squared multiplied by the variance of x. So do spend a moment and check that you can actually obtain that result, which is exactly the same as the result we had when we looked at discrete random variables. So if we move on to an example, this one here, first of all we need to find the expected value of x, so that's something you should be very familiar with. That would be the integral of x multiplied by our probability density function between at the range that we've got, which is 0 to 1, and either using your calculator or writing that out. And do remember, in an exam, if the exam question says show that, you do need to show all your working for this integral. And you should obtain that the expectation of x is 0.4. So we're now having a further story added on here, that we can sell the feed for 1,575 pounds, and the cost of producing a batch is 550 pounds. So we have a new variable, if you like, our variable g of x, which is p, and that is not just x, it's 1575 multiplied by our continuous random variable x and minus 550, because that's the cost of production. So we now have a linear function of x, and we need to find the expected profit E of p, which is simply E of 1575x minus 550, and that will be 1575 multiplied by the expected value of x, which we found is 0.4, minus 550, and that you can verify comes to 80. So the expected profit E of p per batch would be £80. So you might want to pause a moment and just jot this down and think about it. So this is one of those functions that it changes. So we have one particular function between 0 and 1, and one between 1 and 2. And if you recall, to work out the expectation, it would be the integral between 0 and 1 of t multiplied by the PDF for that particular range, plus between 1 and 2, t multiplied by the function that's appropriate there. And you should be able to show by evaluating those that that comes to 19 over 24. And similarly with the variance, we need ET squared minus the mean squared. Don't forget that minus the mean squared. And to find E of t squared, you would be doing that in two parts. The integral of t squared multiplied by the relevant PDF between 0 and 1, and adding on to that the other part of ET squared, which is between 1 and 2, which would be t squared multiplied by t minus 2 squared dt. And remember, you need to work that out and then subtract the 19 over 24 squared, and hopefully you can verify that that indeed is the variance. So now we need to find the expectation and the variance of 10t minus 5. So we now have our linear function of t, and just recall this was the mean and the variance we found. So to find the expectation of 10t minus 5, that would be 10 multiplied by the expectation of t minus 5, and that you should find comes to 35 over 12. With the variance of 10t minus 5 would simply be 10 squared multiplied by the variance of t, and that turns into a rather foul fraction, so it's probably easy just to quote that to three significant figures as 17.3. And that concludes this video.